Thanks a lot for having the opportunity to present my PhD work here today on advancing multi-criteria energy systems analysis. And to begin with, I want to locate these terms roughly in the research landscape. What most of you probably know, energy systems analysis is somewhere in between engineering and economics and operations research. And the main tool used there are energy system models. And these are abstractions of energy systems in the form of equations and data. And they typically optimize the operation or design of energy systems, mostly with a techno-economic focus. So the most commonly used approach is to minimize the overall cost of the system subject to some rather technical constraints. The other part of the title is multi-criteria optimization, which is mainly a subdiscipline of operations research, and it deals with methods and approaches to solving optimization problems that involve multiple objectives or multiple decision criteria. And my PhD is located somewhere where these two areas overlap. Why is that topic relevant at all? I think you all know that climate change is happening, and in order to mitigate that, we need the energy transition. But because the energy transition is extremely complex, we do need decision support. And on the one hand, we have a rather technical complexity because energy systems are large and highly interconnected, involving many different subsystems. And their energy system models are really a useful tool to support decision-making from a rather technical perspective. But the transition is also socially complex in the sense that many different stakeholders and decision-makers are involved in the energy transition, and all of them have multiple and potentially conflicting interests. For instance, there are interests or criteria related to landscape impacts of large-scale infrastructure, or regarding, let's say, everyday life use of energy appliances at home. Or on a high level, the quadrangle of energy policy claims that there is different criteria that are on a high level the main drivers for decision-making and energy policy. And against that background, multi-criteria approaches are a way of dealing with these multiple interests in the energy system models. To look a bit closer into the topic, what methods are there? What multi-criteria approaches do exist in energy system models? I think there's mainly 5 of them. The first one is what I would call a pure ex-post evaluation, where, let's say, non-technical or non-economic interests are just considered after the optimization, so that they're not addressed in the optimization problem directly. The second approach would be the use of, let's say, simple constraints. An example would be a CO2 cap that ensures that a certain performance level is satisfied by a solution. The third one is monetization, where we use or assign a cost factor or price tag to a criterion. An example could be a CO2 price, and then we add that CO2 criterion to the objective function multiplied with the CO2 price. And these 3 are extremely commonly used. They are used in almost every energy system model. And then there's 2 more sophisticated methods, I would say, one being modeling to generate alternatives, and the other one being multi-objective optimization. And I'll mainly focus on these 2 today and explain also in more detail what they are and how they work. And as a spoiler, I can tell you that I also will introduce like a new approach today. Right, let's take an even closer look. What were the specific research targets of my thesis in that context? On a higher level, it was to advance multi-criteria energy systems analysis, both theoretically and practically. And more particularly, on the theoretical side, I wanted to synthesize paradigm strengths and limitations of these 2 approaches, MGA and MOO. Secondly, I wanted to develop a new approach that combines these 2 existing approaches. And on the more practical side, I wanted to demonstrate that these approaches are applicable and useful in various energy system contexts and for various criteria. These are 3 targets I talk about today. Then there are 3 other which I will not talk about today at all. How did I actually address these questions? I worked on 2 papers that deal with multi-objective optimization, then 1 paper that deals with MGA, and a 4th one that deals with that kind of combined approach of the 2. And I will talk about these today, and then there are 2 others which I will also not talk about today at all. And to set the expectation, I will really focus on methods today, so I won't say anything about any specific assumptions or data that underlie the models I'm using. And in terms of agenda, I will start by talking about multi-objective optimization, then we'll talk about MGA, and then we'll talk about the combined approach. And for each of these three pillars, let's say, I will first introduce the concepts and methods, and then I will briefly show some case studies. Right, so let's hop into the first bit of the presentation, multi-objective optimization. In a multi-objective optimization world, we would consider the minimization of, let's say, two objectives. So in the bottom left corner, we have many solutions that are desirable but infeasible. And the top right corner, we have solutions that are feasible but undesirable. And in between these two, there's the so-called Paretofront, which consists of Pareto-Optimal solutions. And these are optimal in the sense that improvements of one objective are only possible when deteriorating the other objective at the same time. And in contrast, this red dot we see here is not optimal because we can still improve both objectives at the same time. The aim of a multi-objective optimization method would be to obtain such a Pareto-Front. And there are various methods to do that. And I decided to use the so-called augmented epsilon constraint method, which works in the following way. Firstly, we determine these Pareto-Front boundaries, the two outermost points. Then secondly, we decide on a desired number and distributions of Pareto-optimal solutions we want to obtain, which gives us these, let's say, caps or thresholds. And then finally, we obtain these Pareto-optimal solutions by solving this optimization problem for each cap. And in this optimization problem, we have basically reformulated the second objective to a constraint, to an equality constraint, by introducing a new slack variable s, which is non-negative. And this one we subtract from the objective function to essentially create an incentive to guarantee Pareto optimality. That's an established method, and I made a new implementation of that in the open source energy system optimization framework Backbone, which I've been using for all the case studies I present today. And I applied that to a number of case studies, and about one of these I want to talk very briefly now. There was a case study where we considered or addressed thermal comfort in a residential building context. And underlying is an energy system model where a physical building representation translates the use of energy appliances into indoor air temperature. And then the so-called predicted percentage dissatisfied translate that temperature into the average comfort a person would be expected to feel in such a temperature environment. And with that model, we try to analyze the connection between the three criteria of costs, emissions, and thermal comfort. A result of that is a Pareto-Front between these three objectives, which you see here. And we can directly see from that the bounds of the front indicate what the feasible ranges are for each objective. So what's the least cost that can be achieved, what's the highest emissions, and so on. And the shape or the slope really tells us about trade-offs between the objectives. But that's very difficult to analyze because it's 3D. So we decided to cut slices indicated by these dots, slices of constant comfort, and project these into like the cost emission plane, which is what you see here now. And from there, it's much easier to quantify trade-offs. So for instance, we can see that here the slope indicates CO2 abatement costs, which would be around 570 euros per ton in this region. Or we can, by comparing the slices, look into potential saving potentials. For instance, we could reduce costs by 1,400 euros or emissions by 2.6 tons by accepting a decreased thermal comfort in the building environment. That's been a very quick look into multi-objective optimization. So let's get to the second topic or the second method, which is MGA. With MGA, I again start by explaining the method. We're back in a one-objective world. Typical energy system model, we have one objective that we want to minimize to obtain the least cost solution. But now in an MGA world, we are also interested into variable values. So not only in objective space, but also in variable space. And then we find that if we were to accept slightly higher, so slightly deteriorated objective values, many different then many different variable values would be feasible. And that's what indicated by this feasible space. And what we do with MGA then is that we define some near optimal space in yellow, which is defined by a slack on the objective, so some deterioration that we're willing to accept. And in that near optimal space, we're looking for different alternatives. And the aim is that these solutions or these alternatives should be very different in terms of the variables that are being realized. So these are systems that are similarly costly, but look very different in terms of what the system features are. And here, one main motivation for that approach is that it addresses structural uncertainties in the sense that there may be criteria or restrictions in reality that are really important for decision makers, but we are not able to capture them in our model equations, or we just weren't aware of them before we started modeling. And this kind of structural uncertainty can really be well addressed by MGA. How is it used in practice? We start by obtaining the single objective minimum, then we define or decide what this extra cost or the slack is we're willing to accept. And in the third step, we generate these alternatives by solving that problem that you see here multiple times. Here we reformulated the objective function, capital F, to a constraint with some upper cap. And then we solve this minimization problem where we introduced as a main objective term the weighted sum of some of these decision variables that we want to find alternatives for. And by varying these weights or solving this problem for different weights, we can obtain different alternatives. That's also an existing method that I made a new implementation of in Backbone, in an energy system optimization framework, and applied it to different case studies. And I will also very briefly talk about one of them, which is a case study where we analyze different ways or options to decarbonize the power, heating, and cooling supply of my university, the University Bochum. And here it was really about exploring ways to achieve a climate neutrality target, which was set by the university administration for the year 2045. That's a result that you get out of that. What we see here on the x-axis is different heat generation technologies in this case. And the y-axis is their respective heat generation. And each dot that you see refers to one alternative we obtained. So we see something like 70 or so alternatives. And all of these alternatives have only 1% extra cost. So 1% cost above the least feasible cost to achieve climate neutrality. And from that, we see mainly two things. We see that some technologies are used significantly in every alternative that exists. So these are must-have features. We have to use these if we want to decarbonize within this 1% limit. But we see that other technologies, or for other technologies, we have a rather broad range of choices. We can use them quite a lot, or we can avoid them completely. And that's really a large room of choices that decision makers have. Right, but we cannot only look into the solutions on such a macro level, look at the whole set of alternatives, but we can also look into some very discrete alternatives, which we see here again, the least cost solution, and then 5 alternatives. And for each of them, we see the heat generation mix shown on the y-axis. And we can already see that these alternatives differ quite a lot in terms of technology mixes and technologies being used. And what's particularly helpful here is that we can directly relate these to some criteria or some interests that the decision makers at the university may have. And they told us, for instance, well, here we see a high diversification of technologies, which can, of course, be a risk mitigation measure in a sense and can be nice. But on the other hand, that can be like an awful lot of work to implement and maintain such a system at a university over decades. And there are other solutions which are the exact opposite. So one easy technology to maintain and to build, but then you're fully reliant on the prices for that one energy commodity. Yeah, and that's like one way of addressing, let's say, hard to quantify interests or criteria exposed with MGA. Right, that was the MGA stuff. So now I want to talk about a combination we developed, which is called Modeling to Generate Near-Pareto-Optimal Alternatives, or MGPA. But before I do that, or to motivate that, I want to draw some interim conclusions about what we saw so far. What we saw with multi-objective optimization, we generated a kind of representative Pareto-front, saw what the feasible bounds for our objectives are. We learned about trade-offs between the objectives and quantified them well. And And for MGA, on the other hand, we saw what technologies are must-haves and what technologies are choices and how large these choices are. And we also saw some very discrete alternatives that are similarly costly, but have very different system characteristics or just look very differently. And from that, I synthesized in a way that, from my view, multi-objective optimization really thinks and lives and works much more in objective space, whereas MGA really thinks much more in variable space. So with MGA, as long as we are close enough to the optimum, we don't really care about objectives anymore, but we really want to diversify, want to be representative in terms of variables that get us there. But then as a major drawback of multi-objective optimization, all these criteria must be known ex ante, they must be quantified, and they must be modeled. And if that's not possible or not done, then I can't do a multi-objective optimization, but I can then still use MGA because everything can be implicit at the time of modeling. Similarly, MGA considers these near-optimal solutions to address structural uncertainties, as I said, and multi-objective optimization doesn't do that. So everything that's not fully Pareto-optimal, not fully efficient is ignored essentially by multi-objective optimization. But then as a major drawback of MGA, we need some ex-ante decision on very fundamental criteria. For instance, in the RUP example, I said, well, we assume a decarbonization target set by the university administration. And that's a very strong constraint, and that's a very strong preference statement and decision that we presume and we just put into the model by assumption. And that decision itself was not informed by our model. So that's kind of some ex-ante decision that we had to do with MGA, which we don't have to do with multi-objective optimization, where we saw like the full range of feasible emission values. And then we can decide, when we see that and we know about the trade-offs, then we can decide on the decarbonization target. And therefore, because they are so complementary in my view, I thought we should combine the two. And we did that by developing this MGPA method, which works in the following way. We start with a Pareto-Front between the objectives. Now it lies kind of flat in the plane. And then with the MGA kind of approach, we're interested into different variable values, which are now on the Z-axis. And then in general, that Pareto-Front will like spiral up in space because in general, the variable realizes different values along the Pareto-Front. So it's not like flat anymore. To then apply an MGA-like version, we need some notion of near optimality, which we defined as this near Pareto-optimal space, which is like slightly behind the Pareto-Front. And we define that by two caps, one on each objective. And then we look for alternatives, near Pareto-optimal alternatives, which are in the objective projection slightly behind the Pareto-Front, but in variable space, they are very different from each other. And therefore, we like preserve that kind of near optimal feature, but at the same time have very different solutions. Practically, we do that by first deciding on objectives and variables. Then we generate the Pareto-Front. Then we define what we mean by near optimal. And then finally, we generate these alternatives by solving this problem. And that's really a combination of the OCMECON and the MGA approach. So we have the objectives reformulated to constraints, introducing a slack variable, which is non-negative, subtract the slack variables from the objective function. And then as a main objective term, we introduce that weighted sum that we saw for MGA. And now changing these caps epsilon 1 and 2 will shift the near optimal space around or make it smaller or larger. And changing the weights will yield different alternatives. That's a method we developed, and we implemented it also in Backbone and used that in the following case study. This is now a municipal level case study or energy system model of residential power and heating supply. And here the aim was rather broadly, let's say, to explore possibilities for decarbonizing these municipalities. And in terms of results, in a first step, we obtained Pareto-Fronts between costs and carbon emissions. That you see here, it's two Pareto-Fronts because it's two different German municipalities we applied that to. And based on that, we can now make an informed decision on a decarbonization target, where in this case, we decided that these small green shaded areas indicate our decarbonization targets here, but ideally that should be done by stakeholders of the municipality, which we didn't do in this case. Yeah, but that's like the informed first preference-based decision we can make with the multi-objective optimization. And then the question is, how do we get there in that region in terms of system variables, in terms of system designs? And that's the point where we look into variable space. This is a very similar figure to what you saw already. On the x-axis, we have different energy generation technologies. On the y-axis, we have their respective energy generation. And each dot refers to one Near-Pareto-Optimal alternative we obtained with this MGPA approach. And what I want to highlight here is mainly three things that all have to do with these green shaded areas. These green shaded areas indicate what variable values we obtained by looking only at the Paretofront. So when we stay within this decarbonization target, but only look at the Paretofront, that already gives us like a small diversification of variable values. That's this green area. But everything that is outside of the green area is that kind of solutions and that kind of diversity we only obtain because we use that diversifying MGPA approach after doing the multi-objective optimization. And there I want to highlight three things. First, we saw, not surprisingly, that the range of choices really increased for some technologies. Secondly, that some technologies that seem to be must-haves when you only look at the Paretofront are not, in fact, because there are near-Pareto-Optimal alternatives that completely or almost completely avoid these technologies. And finally, when we look into, let's say, these discrete selected alternatives, so this line connects the dots that belong to one specific alternative, then some of these maybe potentially very desirable alternatives are not contained in the Paretofront itself. For instance, this green line now indicates a solution that has very